a big part of equilibrium involves ICE tables. And ICE stands for initial, change, and then equilibrium. So we're going to spend a lot of time talking about ICE tables and how to solve problems involving ICE tables. So this is just a simple ICE table calculation that is very typical of something you would see in an equilibrium type problem. So here's my information I was given. A 1 liter flask initially contains 0.298 moles of PCl3 and 8.7 times 10 to the negative third moles of PCl5. I don't have any information about Cl2 initially. Okay, all I was given was those two pieces of information. After the system reaches equilibrium, you do some studies and you find that you have 2 times 10 to the negative third moles of chlorine gas in the flask. And so I want to know what are the equilibrium concentrations of all of these substances, and I also want to know the value of the equilibrium constant. So we set up an ICE table. Now ICE, initial, change, and then equilibrium. And then all you're doing is you're writing your substances across the top here. So that's PCl5, that's PCl3, and that's Cl2. So now we're just going to use the information from my chart, from my problem to fill out my chart. So the problem says that these are my initial concentrations. All right, that's what the problem gives me. And since there's no information given about Cl2, we're just going to assume that it's 0. Okay? So this comes directly from the problem, and this comes directly from the problem. And then the problem also says, oops, went too far. This also says that at equilibrium, we had 2 times 10 to the negative third moles of Cl2. Okay? So again, because we didn't know the initial amount of Cl2, we're putting it as 0. And then at some point during the reaction, we made this many moles. Now we're going to use the law of conservation of mass to figure out what these other spots are going to be. So let's figure this out. Where is the only place that Cl2 can come from? Well, it's coming from the PCl5, right? This must decompose to get Cl2. Because we're assuming that there's none in here initially. So where did it come from? The only place that Cl2 can come from is PCl5. So for the amount at equilibrium to be 2 times 10 to the negative third moles, that means that PCl5 must have gone down by 2 times 10 to the negative third moles. Right? The law of conservation of mass says that matter is never created or destroyed. If there was no Cl2 in there initially, and all of a sudden I've got 2 times 10 to the negative third moles, the only reasonable place it could have come from was this PCl5 decomposing. Okay, so this goes down by 2 times 10 to the negative third. This goes up by 2 times 10 to the negative third. Now the other thing we need to think about is that, again, following the law of conservation of mass, if this goes up by 2 times 10 to the negative third, well, this one's a product as well, involving chlorine, so it's also going to go up by 2 times 10 to the negative third moles. So my change, this one goes down by 2 times 10 to the negative third, this one goes up, and then this one's also going to go up. And so then all we need to do is subtract or add, depending on which substance we're talking about. We subtract straight down, we add, and then we add. But these are just number of moles, right? To do our equilibrium expression, because equilibrium expressions don't deal with number of moles, they deal with molarities, right? You can't plug number of moles into an equilibrium expression. You can only plug a molarity into an equilibrium expression. So we're just going to divide by the volume of the container here. Now the volume is 1, so the units are the only thing that change. The numbers will not. So taking the number divided by the volume gives me my molarity. Number of moles divided by volume gives me my molarity. Number of moles divided by volume gives my molarity. And so if I want to know the value of the equilibrium constant, I just plug my molarities in, and I get a value of 8.96 times 10 to the negative 2. Since K is less than 1, we would conclude that this is a reactant-favored process.